So in part 2 of this unit, we are going to be doing sampling distributions and standard error. So in the first part, we did the sampling methods or techniques. So we, stratified and the cluster and the random selection, that kind of thing, how you get samples. And what we're going to do now is kind of what you do with a sample once you have it. And the whole point of this part of the unit is to basically decide if samples themselves are unusual or not. So think of it this way. You had a standard deviation in our previous units, which tells us, if a piece of data is unusual. What we're going to do in this unit is the whole idea of standard error, which the standard error will tell us if samples are unusual or not. So we're going to be getting the means of a bunch of different samples, and then we're going to get the mean of those means, and that'll tell us if the group of samples is unusual or not, or if a particular sample is unusual or not. So I put this little meme here. Standard deviation and standard error often get confused. Standard deviation is when we're dealing with kind of individual pieces of data. Standard error is when we're dealing with groups of data or samples. But it will become more clear as we go through this. So first of all, what is a sampling distribution? Well, as it says here, it's a distribution of all possible samples taken from a population. And what that means is, you have this huge population. In this unit, we're going to be talking about fish. So you could have, hundreds or thousands of fish in a given pond or even the ocean. We can't take and measure every single fish, but we could take samples of groups of fish and then work with that data. And it turns out that's actually usually good enough. So it's the distribution of all those samples that we've taken, for example, the lengths of fish. And each of these samples has its own mean, which is going to be, our mu, and its own standard deviation, which is going to be our sigma. So every single sample that we take, for example, let's just take a sample of 5 fish. That sample of 5 fish will have a given mean length, and it'll have a standard deviation. We can kind of work with those. So graphing the means will give us a shape, will give us a general idea of where each of those sample groups lives. So for example, you might take a sample of fish and it sits right there in the mean. It's right in the middle of your data set. But you might take another 5 fish and get their lengths, get their average length, and it might sit down here. So depending on the group of fish that you sample, you're going to have bigger and smaller lengths, just like if you'd sampled the fish themselves. The interesting thing about taking samples is that if you take enough samples, the shape will end up being a normal distribution. And it doesn't matter if your fish are all crazy lengths or anything. You could have a weird population of fish, but it turns out when you sample them, the shape you're going to get is actually going to be a normal distribution curve. And this is something that's called the central limit theorem. Which in simple terms means that if we have a population, if we take enough samples of that population and we graph or put the distributions on a curve, it will end up looking like a normal distribution, which is very powerful. And there's a whole lot of videos and higher level math stuff on that, but that's all I really need to know. We can turn any set of data into a normal distribution shape. So why do we need sampling distributions? Well, sampling distributions are important because they provide a simplification to make judgments. And what that means is that you might have a whole population, maybe the whole population of Canada, and if you want to learn a little bit about Canadians, well, you don't want to have to deal with every single Canadian. Sometimes taking groups of the Canadians is enough. Maybe you want to take a sample of people from every single province, or maybe you want to take a sample of people, depends on what you're thinking about or who you want to learn about. So instead of taking the whole population, you might take a sample. So maybe take different groups and put them take different samples of the overall group, just like we did in part 1. And again, what we were thinking about in part 1 is why would we gather information from a sample instead of a population? What's the benefit of taking just some of the people that you're talking about instead of looking at the whole thing? Wouldn't the whole group be a more accurate way of getting our data. And it would be, but the problem is it can be very costly, or it can be, it takes a super long time. So let's break it down into advantages and disadvantages. So why would we gather information from a sample instead of a population? Well, lots of advantages actually. There's low cost. It doesn't cost as much money to just deal with a few groups instead of the whole group. It's less time consuming, which means it takes a lot less time to get samples of a smaller group than to, for example, poll all of Canada, or get the heights of everyone in Canada instead of everyone in Newfoundland, for example, because populations can be too big. Maybe, if you wanted to have a good idea of something about the whole world, what's your favorite food, but you try to poll everyone on Earth, it's going to take a whole long time. And in this case, for sampling, the accuracy of data is higher with larger samples. So you actually can have more reliable data if you deal with samples sometimes than if you try to deal with populations. And because of all these ideas, it takes less space and resources. So you probably won't get a lot of questions on why it's advantageous to use a sample, but it's a good idea for you to understand why it would be better. The disadvantages, kind of the unfortunate side of using samples, is that there's this idea of bias, which means the people that are collecting the samples might just decide that one of the samples isn't good enough and just kind of reject it, and it kind of skews your data one way or the other, right? Or the person taking the information in, the person collecting the data, might have an agenda, which means they might want to present the data in a way that convinces you of something, and so that's easier with samples because they have a choice whether or not to remove entire groups. Second, you can have difficulties in selecting a truly representative sample. What that means is, there's all types of people in Canada. There's people from all over the world, right? If you just poll people in Newfoundland, you're probably going to get a lot of people that have lived in Newfoundland their entire lives and are, for example, strictly Caucasian in a lot of cases. But there are many, many, many nationalities in Canada. And in order to get a truly representative sample, you're probably going to want to go outside of Newfoundland. You might want to go into Vancouver, which is a much higher Chinese population, for example. Or find your Japanese populations, or Indian populations, Pakistani populations. And in Newfoundland, you can get a sample of these nationalities, for example, but it's much more difficult getting a true representation of who lives here if you don't poll the entire country, if you see what I'm saying. So finally, if a researcher is not knowledgeable, then improper techniques might be used. So if the person who's collecting the data doesn't fully understand the process that they're using, but they're just spitting all this data out, then even though the numbers might look like they mean something, it could be just a load of crap. It might just be useless numbers because the data that they were using or working with was useless because they used bad techniques. So you have to be really careful when you're doing sampling, but if you have someone who knows what they're doing, sampling is just as good as getting the information from the entire population. So let's make things clear with a fish example. In this example, we're going to be dealing with the lengths of fish, and it turns out in this example we have a population of 4 fish, so there's actually only 4 fish in this pond, but it doesn't really matter. There could have been hundreds of fish or thousands of fish, but just to keep the number small, we're dealing with 4 fish. And we want to figure out what's the average fish in this pond, how do we make some interpretations of the fish, big fish, small fish, what's unusual, what's not. In any case, we're going to be talking about standard deviation and then moving on to standard error through this example. So first of all, what does this distribution look like? Well, you have 4 fish. One is 1 centimeter, another is 3 centimeters long, 5 centimeters long for another, and 7 centimeters long for the last. So if you were just to take these 4 fish and make a distribution, it would be very simple. The distribution would be a very simple one. How many fish have a length of 1? Well, 1 fish has a length of 1. How many fish have a length of 3? 1. How many have a length of 5 and 7? They all have distributions of 1. So this distribution as it is just flat. I mean, if you remember from an earlier unit, this is kind of just a uniform distribution. because all of them are equally likely to be in the pond. Because there's just 4 of them, the frequency is equal. In this case, it says, what is the mean and what is the standard deviation? Well, the mean length of the fish is 4 centimeters. And if you want to know why, well, you can take 1 plus 3 plus 5 plus 7, add them all up, divide by 4. That ends up being, well, what's 1 plus 3 plus 5 plus 7? That's 16 over 4. It's 4 centimeters. The mean length of all these fish is 4 centimeters. The standard deviation is 2.24. You can calculate in a number of methods. You could use Excel or any other calculator to get that. So just take that as truth for now. The mean is going to be 4, and the standard deviation, 2.24. Try to keep that in the back of your head. So if we were to do a catch and release, you go and you catch a fish of sample size 2. So you go out there and you catch fish sample size 2. That's another way of saying what's called n equals 2, which means every time you go out to catch some fish, you take 2 fish at a time. You keep going until you get 2 fish, and then you stop. And then you measure them and you throw them back. Okay? So it says sample size 2, once you catch 1 fish for your sample, you need to release it back into the pond. So one of your samples, all of these samples that we get, we could end up getting the same fish over and over again, but that's no big deal. We're just going to imagine that we're going to catch as many fish as we can, and we'll fill in this table with all the possibilities of catching these fish. Okay, so for example, if you think of this as a thought exercise. When you first catch, just say your first sample could be 1 centimeter and 1 centimeter. Okay, that's when you catch a fish, you throw it back, you catch another fish, you get 1 centimeter every time. The mean of the sample, 1 plus 1, divided by 2, is of course 1. So that's where this comes from. You do the same thing again. Let's say you go and you catch a fish, and it's 1 centimeter, you throw it back, you come catch another fish, it's 3 centimeters, you throw that back. The total, or mean length, the average length of the fish that you caught is 2, because it's 1 plus 3 over 2, which is 4 over 2, or 2. So you do this, you play this game all day, all right? And we're going to fill in this table. I'll speed things up in a second, but I just want you to get the idea. If the sample size is 2, you're taking 2 fish out of the pond. You're taking 1, releasing it, taking another one, and then you're going to see what the mean of that sample was. So let me read through what's here so you don't get lost, and we'll quicken this up and then talk about what this means. If we were to do this, continue this process, there are 16 possible samples, like 1 and 1, 1 and 3, 1 and 5, 1 and 7, and so on. And we can list them here almost like a sample space. The next thing we're going to do is have a little picture of this, and when we're done, I know I'm jumping ahead here, but I want you to see the full picture. Once we found all these samples, we'll find the mean of each of the samples. Find the mean of each of the samples. Every single one of these samples we're taking, which in each of these have a sample size of 2, we're going to get the mean of all of them. And at the end, we're actually going to get the mean of the means. And that's going to be our standard error. But that's getting ahead of myself. So for example, let's just make some sense of this. Maybe it's a bit easier if you look at it in a visual way. So these 2 fish, this might be our first sample. We fish twice, we get 2 fish. They're both 1 centimeter, so the mean of this is 1 centimeter. We do another little fishing game, and we get a 3 and a 1. Well, 3 and a 1, the average for that is 2 centimeters. Or the mean of that group is 2 centimeters. If you do the same thing for this, pause the video if you need to, what is the mean going to be? Think about that. What's the mean of that sample group going to be? Well, it's 5 plus 1, which is 6, divided by 2, so the mean is 3 centimeters. Now we can play this game all day. What if you wanted the mean of this group? That would be 4 centimeters. And you can fill in this whole page. If you want to practice this, getting the mean of every one of these samples, you could spend a minute or so and get all these means. But on the next page, I've done it for you. Just please don't go forward until you understand what I'm doing. I'm getting the mean of each group. Otherwise known as the mean of each sample. So remember that the sample size, here we have n equals 2, because we've taken 2 fish for every sample. And I keep repeating that because the sample size later is going to be really important. This is the sample size. So I've done it for every single one of these fish. I've done it. We've got a 1, a 2, a 3, a 4, a 5, a 4, a 3, a 2, and so on. We've got all these different means. And these are all the possible combinations of samples. All the possible different combinations of samples, I should say. So if we put all these answers in a table, let's take some time to think about this. These are all our possible samples. That's like our sample space, if you remember from our probability unit, all the possibilities. And these are all the means of all of those. If you don't remember what I'm talking about by sample space, think back to the dice. If you roll a 6-sided dice, what are all the possibilities for your sums, for example? But the important thing here is that every single sample has a mean, and then all of these means come up a certain number of times, all the possible sample means. So how many times does 1 centimeter come up? Well, we see that it comes up 1 time and 1 time only. So the frequency is 1. What about 2 centimeters? You know, you can pause the video and try to fill in this table if you get what I mean. That comes up once, twice, I think only 2 times. And I'll do one more. How many times does 3 centimeters come up? It comes up once, twice, 3 times, 3 times, and then we can keep going. I might as well do the rest with you. 4 centimeters, 1 time, 2 times, 3 times, 4. Let's keep going. How many times 5? 1, 2, 3. I wonder if I have any colors left. And then let's see. 7 comes up once. All right, so if you look at our frequency, we have this kind of pattern emerging, which in fact happens no matter what kind of sample we get. There's going to be this tendency for something to group up in the middle. I've just got it listed in a way that makes that really clear. So the frequency of every mean, the lower means happen less, the higher means happen less, but the ones in the middle happen more often. Let me show you what this looks like as a distribution. So all the same stuff, but this is the important thing, the distribution of the means of the samples. So the distribution, the way that we've distributed the means of all the samples. Now we're not putting the original fish there. Remember, that was a uniform distribution. What we're doing is we're getting all of the means, all of the averages, getting all the averages of the samples, and we're distributing those. And what we see is we're actually dealing with the mean of the means. Take a moment to process this concept, the mean of the means, the average of the averages. That is a very strange concept that it might take some time to process. By the way, what is the mean of the means here? Well, there's a number of ways to get that. First of all, you can get the mean of the means by using this table. If you add all of those numbers up, you get 64, divided by how many numbers there are. There's 16. So the mean of the means is 4 centimeters. A bit of an easier way to get the mean of the means is to remember that if this is a standard distribution, which it is, the mean is going to be right in the center. So the mean of the means, remember, because this distribution is made up of the means, the average of the means is the middle value here, or the mode, or the mean. It's all the same thing. So that's a nice way to work it out too. You know that it's going to be right in the middle. The easiest way to know what the mean of the means is that it's actually going to be equal to the original mean. When we started this question, we knew that the mean was 4. So I'll get back to that in a second. The mean of all the means, the average of the means. In other words, when you get all the means, the average of every single sample, and then you get the average of that, you get the mean of the means. It's 4 centimeters. The symbol is mu with the x bar. The mu meaning the average and the x bar meaning the mean, or also the average. So it's the mean of the mean. It's this like circular idea. Finally, the standard deviation of all the means is 1.58. Standard deviation of all the means. What does that mean? What it's trying to represent is that if you took all of these and got the standard deviation of it, you would get that number, which hopefully should make sense. It's how much this data is spread out, how much the means are spread out from the mean of the means. It's a tongue twister for sure. You got to take some time to think about this. But you would calculate this using, Excel or any other method. You'd take all those numbers and figure them out. And the symbol is sigma with a bar over the x, which means the standard deviation of the means, which is also known as the standard error of the mean, or the SEM. So the standard error of the means is sigma with an x bar on the bottom, okay? It's the standard deviation of the means. It's how much the means are spread out. Now, if you're getting a little bit lost, it's a good idea to pause and go back, okay? But it's the standard deviation, not of the original data set. It's the standard deviation of the means. And the means are all coming from the samples that we took. It's the standard deviation of all these means. So let me just recap. In the beginning, our standard deviation would have been totally different, right? We've got this uniform distribution. It's just, there's not even a distribution to talk about. But once we start sampling, we can actually make it clearer to understand because we get the distribution that we're used to, and then we can apply all our techniques. We can get the standard deviation, we can get the mean, we can get even a z-score or probability of things at that point. Actually more useful than the original data set. So that takes a long time to make some sense of, but hopefully you can pause the video and just sit and think about it for a while. So, as a sort of summary of what you should have picked up there, and I know it's difficult to follow sometimes, so this is a nice reference point for you. Some important things to notice. The population mean is equal to the mean of the sample means. So that's hugely important. I kind of referred to that earlier. Remember that our mean of the means was 4, and our original mean was also 4. Remember, we had 1 plus 3 plus 5 plus 7 divided by 4 in the beginning. That was 4 centimeters. We also got 4 centimeters when we got the mean of the means. Second, the standard error of measurement is the standard deviation divided by the square root of the sample size. So in that case, or in our case, maybe I should put that in a box, that's a formula. It's saying here, check for the fish example, the standard deviation was 2.24. The standard error of measurement was this. So in other words, the standard error of measurement, or the standard error, is the standard deviation divided by the root of the sample size. The standard deviation for our original data set was 2.24. The sample size for our original data set, well, remember we're taking 2 fish at a time for every sample, so the sample size was 2. And so as long as we have the standard deviation and we know the size of the sample, we can get the standard error every time. And what that's going to work out to is 1.58. And what that 1.58 means is how spread out the means are. Not how spread out the original data set is, how spread out their means are. And that can still let us really understand the data we're working with. Finally, our final point, even if the population is not normal, so in the original data set, remember it was a uniform distribution, if the sample size is big enough, or the sample is big enough, in this case we had 16 samples, the sampling distribution will be normal. And once again, this is also known as the central limit theorem. And what that means is that our original data set, we've had this uniform data set in the beginning. If we sample it enough times, the distribution we're going to get is actually going to transform into a normal distribution through just the way the math works, and just the way that things work. And we can then apply all of our normal distribution techniques. Many mathematicians say that that's the most important theorem in all of math. You might not agree, but it's something important to at least point out. So let's move on to some actual practice. Let's do a few more calculations to get this in our heads. So if you're asked to find the standard error, the process is actually quite straightforward because we know what our formula is. And we just did it, but I'll remind you. It's the standard deviation divided by the root of the sample size. We do not need the mean. The mean is going to be the same no matter what. The population mean is going to be exactly the same as the sample mean. So all we need is the standard deviation and the sample size. Standard error of measurement will be standard deviation divided by the root of the sample size. In this case, that's going to be 3 centimeters. You work that out. So let me just remind you what this means. The sample size, for example, 25, means that for every sample that we take, there have been 25 things. So for example, this is lengths, I don't know of what, 100 centimeters. Just say we're measuring the length of something, length of a tree. Let's just say how tall a branch is, or how long a branch is. We're taking 25 branches for each group. We might have hundreds and hundreds of samples, but each sample has 25 branches in it. I hope that makes some sort of sense. Try the other ones yourself. Pause the video and try to get the next 2 answers. You'll find that the standard deviation for this is 5.3. The sample size, there are 100 samples in each group. 5.3 divided by root of 100 is 0.53 years. So this might be the average age of death, for example, of a certain population. We've picked 100 people's times of death, or lifetimes, for each group that we've sampled. And then the error of measure is 0.53. And finally, in the last case, 84.7 divided by the root of 250. If we work that out, we'll get 5.36 kilograms. So what the standard error of measurement tells us is how unusual our samples are. So we can say, all right, 3 centimeters. That's like a standard deviation, okay? Because it is the standard deviation of the means. It means that if we had a middle value of 100, then if we had a sample whose mean was below 3, let me make this clear. Let's just say we have a population mean of 100 centimeters, and then plus or minus 3 would be 97 or 103. Okay, that'd be one standard deviation away. Another standard deviation away would be 94 and 106. What it means is that anything past those points on left or right, if the mean of the sample is below or above those points, we know that the sample is unusual. So if you had a group of branches whose mean was like 92 or something, if your branches, the group measurement was 92 centimeters, you would know that that's a really strange group of branches. Maybe it's kind of an outlier. Or if you had a group of really, really, really long branches that was like 137 centimeters in length, that would be extremely unusual, assuming that we're going with the same, comparing it to this original sample mean, population. Hopefully it makes a little bit of sense. This is a tricky concept. And if you didn't fully understand standard deviation, then you're probably going to have some trouble with standard error. So why should we care? Well, I can tell you a few reasons, but I'll try to make it at least useful for thinking about data. First of all, it tells us if our samples are unusual or unusual. It tells us if our samples are usual or unusual. Unusual means plus or minus 2 standard deviations, or 2 standard deviations meaning standard error, away from the mean. So that's a tricky thing to think about. Your standard error is standard deviation, but it's the standard deviation of means instead of standard deviations of the original data set. So you know if a group or a sample is unusual if the mean of that sample is too far away from the center line. Again, very tricky thing to understand. Hopefully the practice will help you out. Second, it will help us come up with a range of values for our population mean if we only have a sample mean to go by. So we can make some assumptions about the population if we're only dealing with the sample mean. It's called a confidence interval. We'll talk about that in a later unit, so don't worry too much about this. I'll just put a little star on it, but we will come back to it later. So let's wrap it all up. Suppose you need to know the average length of all the fish in a pond. And that's a population. So you sit and you think, how big are all the fishies in this pond, I wonder? But maybe the pond has too many fish. Or you only have, a day to catch some of the fish. You can't catch every single fish because the population is too big. So you can't catch them all, so you go and you catch a sample instead. So instead of getting all the fish, you catch a nice sampling of fish. Or maybe you catch 100 samples of fish, right? But you get a selection of the original population of fish. Then you measure their lengths, and based on that, you get the mean and the standard deviation. So you are figuring out the lengths of the samples, the mean of the sample, instead of the mean of the entire group. Okay? It's the sample, not the population. Because you're using a sample, you'll need the standard error of measurement, which means that whatever you do, you're going to have to deal with the original standard deviation, but you have to divide it by the sample size. So remember, we were trying to get the average length of all the fish in the pond. We didn't do that. We got the length of, or the average length of the sample. How does that help? Well, in this big text, sorry that I have it all in capitals here, we can be reasonably certain that the average length of all fish in the pond is between about 2 standard errors above and below the mean. So if this is our standard deviation, our standard distribution, if this is our mean, then we have -1 standard deviation, -2 standard deviations, 1 and 2. As long as we're dealing with samples and we've done our math correctly, we've got our standard errors done correctly, as long as we're within this, I should use green, as long as we're within 2 standard errors below and 2 standard errors above, this is all usual. So we can actually make a lot of deductions about the average length of the fish as long as they're within this range. You could say, okay, I only have a sample, fine. But as long as my sample, as long as I'm not going plus or minus 2 standard errors above the mean of that sample, that's probably going to represent the group pretty well. Like, that's a really big spread. Anything below 2 standard deviations, we can say that those fish are probably not in the pond. And anything above 2 standard deviations is also saying it's probably unlikely that the actual population of fish has a mean above that point. This is a bit tricky. I understand that. But take some time to try and understand it, and it'll do you well. We'll do one more little example here to make it clear. Let's say that the sample mean is 20. Okay? By the way, if you're confused right now, just take a moment, clear your mind. Let's start again from here, and this is kind of a very cut and dry example that can help us understand, okay? Let's say that the sample mean is 20. So the sample mean is 20 centimeters. The sample standard deviation is 6 centimeters. Pretend that our sample size is 4. That means for every sample that we take, we're taking 4 fish. Calculate the standard error of measurement, which is also known as sigma x bar. So our standard error of measurement is the standard deviation divided by the root of the sample size. Very simple calculation. 6 divided by root 4, which is 6 over 2. I don't even need a calculator for this. 6 over 2, which is 3 centimeters. What that means is that our standard error, our standard deviation of the means, is 3 centimeters. So we can be reasonably certain that the average length of all the fish in the pond is somewhere between 2 points. What are these points going to be? Well, 2 standard deviations below. So 20 minus 3, that's 2 standard deviations below. That's 14. 2 standard deviations above, or 2 standard errors above, it kind of means the same thing once you've done it. 26. So even though we're dealing with a sample, we can be pretty sure that the average length of the fish in the entire pond is between those 2 points. So you've got 14 centimeters on that boundary, you've got 26 centimeters on that boundary, and the mean itself is 20 centimeters. So once again, let me give you the big picture. We don't know the population mean. We can't sample, we can't get the length of every single fish in this pond. It's just not practical. But if we take enough samples, and the samples are representative enough of the overall population, we can make a really good argument for what kinds of fish live in this pond. You know, we know that the 20 in the middle is the mean. That's pretty reliable. We know that 1 standard deviation away from the mean is 17 centimeters. We know that 2 away is 14, and on the other side is 26. We can be sure, almost positive, that all of the fish in the pond are going to live in that region between 14 and 26, even though we don't know the lengths of all the fish. Hopefully that's a little bit clear to you. One more practice. Let's say the sample mean is 20. That'll be the exact same as the population mean. Standard deviation is 6. We know the sample size is 9, so every sample took 9 fish this time. Standard error of measurement is going to be standard deviation divided by the sample size. That's 6 divided by root of 9. In this case, that's 6 over 3, which is 2 centimeters. That means that even though we're dealing with a sample, we can be reasonably sure that all of the fish have a length between 2 standard deviations away from the mean. So the mean is 20 centimeters. Take 2 away from that on both sides. 20 minus 2 is 16 centimeters. And add 2 on the other side, you get 24 centimeters. We can be reasonably sure that even though we only have a sample, 95% of the fish in that pond should live between those 2 boundaries. I hope that makes a bit of sense. So, as a summary here, when we increase the sample size, we have a better idea of the population average. There's less spread. So we can be more and more certain of where those fish are, how long those fish are, and so on. In our original example, example 1, that was the example and this is the practice. Our sample size was 4, which means we had a bigger spread. If you don't know what that means, let me show you. If when the sample size was 9, we had a smaller spread. Final note on that. The larger your sample size is, the better an assumption we can make on how long the fish are. Notice that this gave us 14 and 26. That's a really big spread compared to 16 and 24. The more fish we sample, the more certain we are of what the original population is, or what the length of the original population is. Take some time to sit and think about that for sure. Long story short, bigger sample size, better idea of the average. Bigger sample size, closer to the actual population data. Those are the big ideas. Finally, this is the last slide. Standard error of measurement doesn't just work for fish. You know, it's not just for calculating or figuring out lengths of fish. You can figure it out in all sorts of applications, from the auto body industry, like size of tires and lengths of all sorts of stuff. I wish I could come up with an example right now, but my mind's blanking. I want to do this sort of quickly. So we can find probabilities using the standard error of measurement if we modify the z-score formula. So let's just say in the bottom case here, this is about fish, but it could be about tires. Okay, let's just say we had an industry that was making tires for cars, and you wanted to have the tire have a certain diameter. Make sure that your tires are not faulty. Okay, you don't want to have to test every single tire in the entire factory, so you take samples of the tires, and that is enough to be certain about the tires you're making, even though you're not testing every single tire. So what I mean by finding probabilities is, for example, in this case we had the fish in a pond have a mean length of 20 centimeters. The standard deviation, given by this question, is 6 centimeters. It wants to calculate the probability that a random sample of 4 fish, that's a sneaky way of telling us the sample size, four, will have a mean length that is below 18 centimeters. The mean length, 18 centimeters. So by probability, it's like if we're sampling the fish, how likely is it that the fish in this pond, on average, are below 18 centimeters long? And we can do it in the exact same way as we did in Unit 4. We just modify the formula. So look at this. The z-score, this should be the z-score formula you're familiar with, but instead of just standard deviation on bottom, you've got your standard error of measurement on bottom because it's for a sample. It's called a modified z-score formula. So let me show you how it works. If you want the probability, remember that the first step is to get the z-score, and the second step is to get the probability. So follow me here. The first step is the z-score. The z-score, in our case, is not the data value, but the mean of a sample minus the mu, the mean of the whole thing, over the standard error of measurement. So in this case, the mean length is 18. It works just like a data value. The mean of the entire group is 20. And then you have the standard error of measurement, which is the standard deviation divided by the root of the sample size. What we have here is negative 2 on top, 6 divided by 2, so 3 on bottom, negative 2 over 3, which is negative 0.67. Let me scoot this over here. All right, let me make it bigger. Negative 0.67. So our z-score for the mean length is going to be negative 0.67, which is about right here. So what is the probability that a random sample of 4 fish will have a length, a mean length? You know, the mean length being the coming from the sample that'll live below this point. Probability that the average group size is going to be below that point. Well, we've got our z-score, so we just need the probability up to this point, up to that z-score, which we've done in the previous unit. Just use a z-table. You can use a z-table. You can just calculator that. You know, use an online calculator, use an Excel calculator, whichever way you want. I'm going to use the online calculator. So in this case, I want to calculate a probability based on a z-score. So my z-score was negative 0.67. If I calculate this, it's going to say, what's the probability of the data value lying beneath the z-score? I know myself, I'm actually talking about the mean of the sample set in this case, the mean of the sample, which is the same thing as talking about a data value in this case, as far as the formula is concerned. And it's going to be this number, 0.25143. 0.25143. So that is my final answer. So to recap, that is the probability that if you take a random sample of 4 fish, like you just dip into the pond and take 4 fish, the probability that the averages, their average length as a group, is going to be less than 18 centimeters. So the mean is 20 centimeters. Let's not forget that. The likelihood that if you dip into the pond, take out 4 fish, and get their average length, how likely is it that that average length is going to be below 18 centimeters? That is about a 25% chance. I hope that makes a bit of sense. If you didn't fully understand Unit 4, you're going to have a lot of trouble with this one, but I hope that things are clear. There are a number of extra examples that I'm going to put online that can help you here. So that's what the rest of this video is going to be, is trying to help you understand this topic better. So let's give you a few resources. So the first resource really that you should go to is found under Unit 5. You go into Unit 5. This might look a little bit different when you see it, because by the time I post this I might have added a few things, but it'll be here in here. Under Helpful Resources, you'll see Sampling Distributions Handouts Supplement. So not every student loves watching through the video on this stuff, and they would rather see more of the content written out. So that's what I've done. I've done kind of a supplement to this, which is the same sort of information given a different way, and it's all about sampling distributions, which at the end of the day is all about standard error. And it talks about what the standard error is. It gives you the formula again in very clear terms, tells you the difference between standard error and standard deviation, and then gives you a few practice examples, okay? Finally, on the second page, it talks a little more about the central limit theorem, gives you a link to a video, which I'm also going to put on D2L, and then some more practice on the z-score and probability stuff that I talked about a little bit, just a couple minutes ago. So this whole supplement is 4 pages, 2 of which are a short introduction and explanation, and then the other 2 pages, 3 and 4, are examples. I'll have the answers put in here once you see it. But you'll see that there's an example on probability, and then another example on probability that goes between 2 points, okay? So that's your supplement, and again, this will have answers by the time you see it. The other 2 things are videos. One is a very short video which explains the difference between standard deviation and standard error. So I very much recommend that you watch this. It's only 3 minutes of your life, but it could really help you understand what the difference is between these 2 topics, and most students get them confused. So it's a good idea to get a good leg up on that. And finally, the third video, the central limit theorem, that's an optional video. You don't have to watch it, but because it is 10 minutes long. But if you want to know really what's happening behind the scenes for what we're doing here, this is a really great video to watch. I totally recommend it. It could really help your understanding. But in terms of what's expected for this unit, that's about it. I mean, of course, there's going to be an assignment, and there's probably going to be a lab, but that's it for the end of this video. So let me know if you have any questions. I'm always willing to help. Just fire me an email and we can sit down and talk it through. But in any case, take care of yourself, and we'll see you in the next lecture.